At the end of class, I'm going to give back your proposals. Actually, the 3 TAs handled this differently. 2 of the TAs should have sent you remarks by email. And 1 TA wrote the comments on here. For the most part, the comments are just, that looks fine, because that's pretty much what most of them are, okay? So unless you got something from a TA saying, come and see me because I think the topic isn't right or something like that, then you can just assume everything's fine. The only concern maybe is sometimes they'll say, they might have pointed out you missed a reference or something like that, or maybe they thought the topic was too broad. But for the most part, the comment is, good work, just keep going, okay? And I'll hand these back at the end, but again, there's not, if the comments are emailed to you, there won't be anything on here anyway. All right, so I want to continue talking about clustering. And where we left off was we had talked about finding the levels, the upper level set of a density, and we do that just by doing an estimate of the density. And we saw that we could either cut it at one place and just find those clusters, or we could find the whole level set tree if we want. One thing I wanted to mention is what kind of theoretical guarantees are possible. Is there any sense in which this set is close to this set? And to do that, we have to ask, how do you measure the distance between 2 sets? Well, there's many different metrics on sets. And so there isn't one right one, but I'm going to describe to you one of the most commonly used metrics in statistics, machine learning, computational geometry for measuring the distance between 2 sets, A and B, which is called the Hausdorff distance. This is just a good thing to know about in general. So here's A, here's a set A, here's a set B. There's many different ways to measure the distance, but the Hausdorff distance is defined as follows. It's the smallest epsilon. I'll just write this down first, and then I'll explain the terms. It's the smallest distance, smallest epsilon such that A is in B plus epsilon and B is in A plus epsilon. But what is this funny plus? A plus epsilon just means enlarge the set by epsilon. That is, take each point in A and put a ball. Now you already used B, so I can't use B for ball. Let's just call it ball. Right, so in other words, if this is a set, imagine taking each point in here and putting a ball of size epsilon. Then that just, what are you going to get? You're going to get a slightly enlarged kind of set, right? And so what we're asking is, how big do I have to grow A till it contains B? And how big do I have to grow B till it contains A? The smallest epsilon for which that's true is the Hausdorff distance between those sets. So that's a measure of distance between sets. And it's not the only one again, but it's a very commonly used one. And so the question is, can we guarantee that L hat is close to L, for example, in this Hausdorff distance? So this was one of the first questions people asked in density clustering. And the answer is not always, because some level sets are intrinsically difficult to estimate, so difficult that you really can't estimate them well. Let me give you an example of what I mean by that. Look at this level set. So this is a T, and by level set I always mean, bigger than or equal to, upper level set I should say. Question, if I move this T a little bit, what happens to that set? It just changes by a small amount, right? In other words, the Hausdorff distance between these sets when I go plus delta or minus delta is very small. That's a stable level set. But you can see if I look over here, look at this level set. If I come up above T, I get this set. But if I drop T a little bit, it's the empty set. That's an example of a level t where it's very, very, very hard to estimate that level set. A slight fluctuation in t completely changes the set. So we can only estimate the stable level sets. And what this theorem at the bottom of page, I guess it's the top of page actually 11, is that assuming we're at a stable level t like this, and I see I'm missing the bias term, the Hausdorff distance between this and this is of order, and there's a bias term missing in the theorem, plus order I'm writing this out for a kernel density estimator. The same thing would be true in general. What this is saying is that, in fact, this is of the order this is just basically how far p hat, the maximum distance between p hat and p, as long as that's small, the Hausdorff distance between these level sets and the clusters will be small.
So I'm actually not getting intuition on this case where the level set's going to change a lot. I mean, the connected components will.
No, the level set will too. Let's look at t plus, this is t. Let's look at t plus delta. The set is here. Now, sorry, you're right. No, you're right. That was a bad example. You are absolutely correct. I was doing the lower level set, not the upper level set. I have to flip this upside down. Let me do a better example where I have, thank you. There. Yes, thanks. I was thinking lower level set. For upper level set, you can see here, if t is below here, I get this. This is included in the level set. But if t goes up a little bit, this gets completely erased. Yeah. So, and by the way, the proof of this theorem is right there. But just wanted you to see that estimating the level set clusters is related to, not surprisingly, estimating the density. And since we already know there's lots of results we have about estimating densities well, that tells us we should be able to estimate these level set clusters well. OK, so far, just to review, we've talked about two ways to get clusters from densities. One is to use these modes, and the other one is to look at these level sets. And we'll get to k-means clustering in a minute. I want to mention one more thing about density clustering that's become kind of popular lately, which is to produce these really interesting plots that help you visualize the strength of the clusters. And these are called persistence diagrams. They're actually used for more general things, but I'm only going to use it for talking about these density clusters. And there's a very nice paper about this I refer to here, Chazal, Gribus, Udo, and Scriba, that you can find online very easily if you want to see. There's a whole paper about what I'm going to talk about, but I'll just give you the general idea, and it's explained in this picture. Let me explain this picture to you. So suppose you decide to do clustering using the density, and you want to kind of summarize the clusters you're finding, especially, remember, we'll be doing this in multi-dimensions. I keep drawing one-dimensional examples where you can look at the clusters, but it might not be possible to do that, right, in 3, 4, 5 dimensions and so on. So what this diagram does is the following. I'll try to mimic what I have in the notes fairly closely. What we're going to do is, as we move this level, we're going to start up here, and we're going to think about these level sets, these clusters. So when I start up here and I come down, you can see that this cluster, or this level set, is born. That's called the birth time. So it's kind of funny because time is going from higher to lower, so we're kind of going backwards in time. And That's only because the way these things are often done, they're done to functions from the bottom up. It just so happens for clustering, we're working from the top down. But think of this as time, even though it seems like it's going backwards. It's going from big numbers to small numbers. There'll be a birth time here. Okay, and now as I come down, you can see that I'll come down further and further. I don't know why I numbered them the way I did, but this, as I come down like this, lo and behold, there's another time where this is born. That cluster has a birth time, right? I keep going down, and then there's a third cluster, or level set cluster, that has a birth time. But then there comes a certain point of time, and there's a birth time there. There will come a certain time here where these two clusters merge. And at that point, what we're going to say is this one died, and this one continued. This is called the elder rule. The cluster that was born first, I mean, these are merging into one cluster, and just by convention, we'll say whichever one started first is still alive, and this one has died when it merged into this one. So what's going to happen is as you go down, every one of these modes is going to eventually have a birth time and a death time. And I've drawn that for you. So this is born here and it dies here. This is the birth time and the death time. And can you see how that's something about like the statistical significance almost of that mode?
So just elementary, so the global mode dies 0 to 0.
This guy is always alive. That's the biggest mode, right? He never dies. This one had a very short life. This one, if I've drawn it well, yeah, this one's alive until here. Look, then it merges. So what these vertical bars I'm drawing for you are showing you the birth and death times of that cluster. And so the way that they represent this in these diagrams is for each one of these guys now, I just put the birth time and the death time on this axis. So this, let me make sure I get the right one here. I just don't want to get them backwards. So something, what's going to happen, you're going to get dots. This is called a persistence diagram. The nice thing about these diagrams is you can take data of any dimension and summarize its density clusters with this two-dimensional diagram. The diagram is always two-dimensional. And what happens if a cluster has a very short lifetime? That is, the birth time is very close to the death time. It's going to be near the diagonal. So the important clusters show up here, and the less important clusters show up here. And this is something that, again, it was proposed by in this paper by Chazal. It hasn't been used very much, but I think it's actually a very, very useful way of visualizing the cluster structure of the data. So that was just one extra thing I wanted to tell you about. Something else that I won't go into detail till later in the course, we're going to talk about the high-dimensional bootstrap. And I mentioned this R package, by the way, that we have at CMU TDA. If you can do this in our R package, it's going to give you a pink band that looks like this, which is showing you which of these are statistically significant. Which ones are significantly different from 0? How is it doing it? It's using a bootstrap calculation. We'll talk more about that, though, when I get to the bootstrap. Okay, I just wanted to say that in case you try this out and you're wondering what this thing is that appears on your thing. You can think of this as saying these are significant clusters and these are not significant clusters.
The birth time is larger than the last time.
Why is the birth time larger than the last time? Yes, that's because, so birth and death are maybe not the right terms here, because we're starting at the top, and the time is, let's suppose that the height of this density is m, and the height of the density is 0. So time is going from a big number to a small number. We're actually going backwards in time. Maybe I shouldn't have called it time, but height. Just call it height. It has a birth height and a death height. And of course, it has the birth height. It still sounds funny because kids aren't born tall, right? But think of that, what was that movie, the Benjamin Button or something like that, where the guy ages backwards in time? The terminology comes about just because there's this field of topological data analysis, and usually they're studying functions where you're looking at the lower level sets, not the upper level sets. And so the word time there makes a little bit more sense. It's just that for density functions, it seems backwards, but maybe I should just call it something else other than time. Because yes, this is something that's dies before it's born. Okay.
I have another question.
Yeah.
If I give a t time here, then how do we classify the data at the bottom? Which cluster it belongs to?
Like something here?
Yes.
Okay, so remember there's these different approaches. If you do the mode clustering, every point belongs to exactly one cluster. If you do this level set clustering, you have two options. One is some people want to look at the entire clustering structure. So you don't assign points to clusters. You look at the cluster tree or this diagram. If you just cut across this way, you're right. There'll be points which are not in any cluster. Those are considered unclustered points. It really depends on the application. Okay, any other questions? Yeah.
So how is this going to relate to our choice of bandwidth?
Well, if you use the small bandwidth, let me tell you what would happen. So this is actually kind of interesting. Suppose I take a tiny, tiny bandwidth. Well, we know what's going to happen, right? You're just going to get spikes at the data points. So what you're going to get is just, really bad estimates of the level sets. What would end up happening over here is you'd have a bunch of clusters with actually long life lengths. However, if you now check their significance, you would see that none of these are significant because there's so much. When the h is small, the variance is so high. This is why I'm assuming first you've done something to choose a good bandwidth, like cross-validation or something like that.
So you can't use this basically. Oh, I'm sorry. You can't. So this won't make your bandwidth choice irrelevant, but it will show you if you've chosen a pattern.
Actually, so we have a paper about this. I didn't want to get into this because it's getting a little bit on the edge, but we do have a paper where we suggest doing this for every bandwidth and choosing the bandwidth to maximize the number of significant clusters. So but that's kind of it hasn't been an accepted idea yet, so I didn't want to mention that. Yeah?
How is the significance defined?
It's through the bootstrap, but I can talk about that when we get to the bootstrap. But basically, this quantity is a key underlying idea in all of this, is how well can I estimate the density in the L infinity metric. And so we can use the bootstrap to find a number, let's say z alpha, such that the probability that this is less than z alpha is about 1 minus alpha. And then it turns out that essentially this number becomes the size of the band. Because what that says is fluctuations of this size you can't distinguish statistically. So any little bump that's of size smaller than this can't be considered a significant mode. So what's happening, I left out these details because we haven't done the bootstrap stuff yet. But basically we just determine a number like this from the bootstrap. We're getting an L infinity confidence set for the density, and that becomes the way to judge whether a cluster is significant or not. All right, so that's density clustering. I started with density clustering. It's sort of not traditional to start with density clustering. I think it's one of the less traditional versions of clustering. There are, out there in the world, you take anything, right? Classification, there's people who love support vector machines. There's people who love neural nets, whatever. Same with clustering. You go into the clustering world, there's people who are married to k-means clustering. There's people who love density clustering. So it really depends on the person. But I wanted to start with density clustering because I do think it's one of the most well-founded methods in the sense that there's a really clear population quantity that you're really studying. But it's not the most common version of clustering, at least not in the ML and statistics literature. The most common one is k-means. We've already talked about k-means at some point, didn't we? Didn't we talk about it? And was it? Yeah, when we did VC theory, we talked a little bit about k-means. You remember that? And most of you have seen k-means. So let me just remind you about what k-means is and what its strengths and weaknesses are. How many of you have done k-means clustering? See, that's, I would say, it looks like maybe 90% of you, right? So it's by far the most popular version of clustering. And remember what it is. So let me remind you how it works, is we have to pick a k, which will be the number of centers we're going to do. And then you have to pick starting points. A common method is to pick random points. So maybe I'll pick this point. Oh, let's say I'm lucky and I pick these three. And then the next step of the algorithm is to assign every point to its closest center. So these points would all get assigned here. These points would all get assigned here. Well, what would happen here, actually? This is a bit tricky, right? These points would all get assigned here, but maybe this could have been assigned here. Depends how close it was. And that creates a partition of the space, which is called a Voronoi diagram. The Voronoi diagram is a set of polygons which just shows you that every point in here gets assigned to this center, every point in here gets assigned to this center, and so on. Then remember what the next step is I take these points and I take their average, and that becomes the new center. I take this average and I get a new center, and I take this average, I get a new center. And then we start again. We reassign the points and compute the center and repeat. And what are we trying to do? We're actually trying to find k vectors, C1 hat to Ck hat. And this is really just an incremental version of trying to minimize the distance between yi and its closest center. This is the minimum over the centers. We're trying to find, in this case, 3 centers, so that when I take the distance from each point to its closest center and I average that, I want to minimize that. Call that R of C hat, R hat of C hat. And the algorithm that you've learned, that iterative algorithm, usually called Lloyd's algorithm, is some sort of, with a random start and then some sort of iterative approach to try to minimize it. However, does it actually minimize it? No, because this has multiple minima, and it's in fact NP hard to minimize this. So taking random starting values and running this, you'll get an answer. You'll get a local minimum. But if you take other random, try it again, take random starting values and run it, you might get a different solution. And so people typically take many random starts. So the population version, and we talked about this earlier in the course, is what you're really trying to do is you're trying to find a set of vectors. The C here refers to the collection, C1 to Ck, which is the expected value of y. It's exactly the same thing. But with a population, this is just the population version, replacing the sample average with the expected value. This is in some sense just this quantity, the sample quantity is just approximating this quantity. And the guy that minimizes this, if we call this one C hat and this one C star, there's some hope that maybe this is approximating this. So I think this is all review because it looks like you've all done k-means clustering before. And it's, this is the nice thing about k-means clustering, I have to say, is it's very simple, it's intuitive, it's quite fast, it's easy to do, it's built into almost every software, and even if you had to write it yourself, it's pretty simple. But there are problems with k-means clustering. First of all, as we saw, this is NP hard, so we're not really minimizing this. Second of all, even if we are minimizing it, what does it say? What is the minimizer of R hat? How does that relate to that? How does the minimizer of R hat relate to the minimizer of R? Well, we did that actually when we studied VC theory as one of our examples. You remember that? Is that? I think we did it, didn't we? Does anybody remember this? Thank you. So the fact that this is small, less than or equal to, I'm going to say square root of k over n, if I remember correctly. Let's just put in something of this order, I think. I'll have to check in a minute. That came from VC theory. That was one of our examples when we did VC theory. That the empirical risk and the true risk are close with high probability. Also, that means, just like in classification, that therefore if I minimize this, I'm approximately minimizing this. That is, the risk, the true clustering risk of the guy that you estimated from the data is not much bigger than the risk of the best solution. This rate we better check in a minute, but it's in the notes later on, so I'll check it. Just like for classification, right? We said if the empirical risk and the true risk are close, then if I minimize the empirical risk, I'm approximately minimizing the true risk. However, does the fact that the risk of C hat and the risk of, say, the best one, C star, are close, does that mean C hat and C star are close? The answer is no. This does not imply that C hat. And the reason is there may not be, when we're minimizing this thing, the minima may be very ill-behaved. This is not a well-behaved function. You would need extra conditions to ensure that this is minimizing, that the risks being the same means that the centers are the same. You can have very unstable situations where you can switch the centers quite a bit without changing the risk very much. I'm going to show you examples of that in a few minutes.
Since these are set, so how are we defining those two?
I meant like in Euclidean distance.
Like the average Euclidean?
No, this is a set of vectors. This is a set of vectors. I want to say that every one of these centers is close in Euclidean distance to one of these and vice versa, for example. So despite the simplicity of k-means, there's already two problems. We don't know if we're really finding the minimum. And even if we are, we don't know if that's approximating the population quantity. But there's a third and deeper problem with k-means clustering, which is even if I could solve this population problem, suppose I could tell you, here are the k centers that minimize this. It's not clear that's a clustering in the sense that we usually mean a clustering. There's lots of examples where the k-means solution just isn't what we mean. And here's one called the Mickey Mouse example. Suppose I have a distribution. I'll try to draw something that looks like Mickey Mouse. Does that look a little bit like Mickey Mouse? And imagine a distribution which is uniform over these three sets. Now suppose I ask you what is the, and suppose I tell you k is 3, and I ask you what is the population answer? I've given you the true distribution. You don't even need data. You can just say which thing minimizes this. The solution is the following. The solution is to put these. This will be all part of cluster 1. This will all be part of cluster 2, and this will be part of cluster 3. And that's not necessarily a bad solution, but I don't think it captures usually what our intuition is of what we would mean by clusters in this case. We're calling this a cluster, and this a cluster. And somehow it just seems like maybe the k-means criteria isn't capturing here what we even mean by a cluster. Whereas, for example, the density clusters here would be pretty clear. The density clusters would be exactly 3 of them. 1 here, and 1 here. You know, it would be exactly what you were expecting.
Well, maybe we're getting there, but I mean, so in classification, right, we have this notion of a margin, right, which we use to find more robust classification methods, describe more robust classification. It seems like here, what we may be interested in is something like a margin between the clusters.
That's true. If the clusters are approximately spherical and well separated, then this won't happen. Which is some notion of, you might think of that as some notion of margin.
But I mean, still, with these clusters, right, that we would get just with the means, you know, the means idea, right? I mean, the distance between points in the clusters, right, they get arbitrarily close.
Yeah, that's what I'm saying. If they were well separated, then we wouldn't have this problem.
Oh, well,
Yeah.
right. But I mean, even if you do have this problem, though, right, it seems like there's some kind of clustering that is described in terms of maximizing the margins between the clusters, right, that would give us the intuitive cluster.
I don't think so. I mean, density clustering will work, but I don't think you're going to fix k-means clustering here. Because you see, the difference there is you have labels when you're dealing with the classification problem. This is a little bit of a chicken versus the egg problem. If you knew where the clusters were, you could enforce a margin condition, but we're trying to find the clusters. So it's not as quite as easy. These unsupervised problems are a bit trickier that way. Yeah. I mean, another famous example where k-means clustering, whether you consider this it's not clear whether it's a success or a fail, but suppose I remember the example I did with the data were on a ring, and I did say k equals to 4. Well, it's going to cluster it. It's going to pick 4 centers, maybe like this, and you know, it'll do this. And maybe that's the best you can hope to do in a situation like that. Or again, if you looked at the level set of the density, however, you would perfectly recover the ring. So that's a case where density clustering works very easily. There are attempts, however, there are ways to, well, actually, let me come back to your question, because there are ways people have proposed to try to fix k-means clustering, which to do post-processing. So for example, here I could find, say, four k-means clusters, but if I had some way of merging clusters, like if they're close together, I would reconstruct the ring. So k-means clustering with some extra work could still do something that we might consider to be approximately a good clustering in some sense. But just k-means clustering, standard k-means clustering, the important thing is to be aware, it's kind of looking for spherical, well-separated clusters. That's when it tends to work well. OK. So the point here is that the simplicity of k-means clustering is good, but the price to pay, this doesn't always work well. Yeah, so I've got that Mickey Mouse example. You can see it very explicitly on page 15. But to be fair, I wanted to also try it on some examples where it seems like it maybe is doing something good, because I'm going to tell you, I use k-means clustering quite a bit because it is so easy to do. Here's a really interesting example on page 17. I've mentioned this example once before, where we have supernovas, which are these stars that explode. And what we have are their light curves, which show you the brightness of the supernova over time. And I think I mentioned that there's different types of supernovas. There's type 1a, and there's other types of supernovas. And what I did was, the data in this case are the curves. But you can just think of them as a big vector. And then I just handed it to k-means clustering, and it actually did something really good. So this is actually pretty cool. So see if I'm not sure how well I showed you, but what I did is I clustered the data without knowledge of what type of supernova it was. How many? Let me just see what I used for my k. Yeah, figure 15 shows data where we apply k-means clustering. I took k equals to 4. And so what ends up happening, it's maybe a little bit hard to see, but I'm getting 4 sets of curves, right? I'm applying k-means clustering to these curves. And I just arbitrarily set k equals to 4. But I happen to know now which ones are type 1a and which ones are not type 1a. I didn't use that information when I did the clustering. I just blindly applied k-means clustering. Then I put colors on here to indicate which type of supernova it was. Black is a type 1a, and red is the other type. And it really does a very good job. What it's doing is the cluster 1 and 2, you can see, are both type 1a supernovas. There's a few red curves in there, but not many. So it has somehow correctly identified the type 1a supernovas with a very few mistakes. It split those, the type 1a, into 2 subgroups, and it would be interesting to look more closely and see, is there really a difference between these 2 groups? I don't know the answer to that, actually. And then the non-type 1a showed up here, and you can see it's almost perfect. I don't think there's a single type 1a supernova that got classified as other. And again, it split that into 2 groups, which do seem to be qualitatively different. So this was an interesting example where I just threw the data in, ran it, and something sensible seemed to happen. It seemed to actually produce meaningful clusters. All right. So let's now start to address some of the problems then with k-means clustering. As I said, it's simple. It works well in some cases, but there are these problems. And let's start with the first problem, which was, how did we pick the starting values for k-means clustering? If this was a nice convex minimization, there would be no problem, right? I could pick any starting value, and there'll be a unique minimum, and then we converge to the minimum. But the function that we're minimizing is not convex. It has many minima, and we're going to get different answers depending on where we start it. OK, so the most common method is random starts. And that's not necessarily a bad thing to do. And if you do that, people will generally do this many times. Pick k random starting places, run k-means till it seems to converge, repeat many times, and choose the best one. Just to see, though, how easily that can go awry, if you look at figure 17, what I've done is I've taken a mixture of 9 normal distributions. Okay? And what I do is I'm telling the algorithm k is equal to 9. So we're in good shape. Now, I pick 9 random numbers to start it, and I run the algorithm and see what I get. And you can see, I'm not sure how well it shows up here, top left is the data. The top right is the k-means with random starting values. And those colors didn't really come out so good. In fact, that's not even correct, because what typically happens is it doesn't work very well. Because when is it going to work well? It's going to work well if I pick a starting value here, here, here. In other words, if I pick exactly one starting value from each cluster, it's going to work fine. But you can see, when you do this, if you work out the combinatorics, what's the probability that I get exactly one from each of these things? It's not very high. There'll be a good chance you might get 2 here and nothing here. And you're going to get bizarre answers in that case. So even in a fairly simple problem like this, you can see random starting doesn't necessarily work very well. So there have been many, many, many different proposals throughout the years for how to pick starting values in k-means clustering that are maybe we will improve on random starts. I want to mention what I think is the most popular now, which is k-means plus plus, which has some nice properties, but also some potential problems. Who here has used k-means plus plus? OK, maybe 4 or 5 people. It's a very simple idea. In fact, I think people did this for a long time before it occurred to anybody to give it a name and prove something about it. Okay, and it's due to Arthur and Vasilevitsky in 2007. And let me just explain the algorithm by drawing a picture. let's suppose k is equal to 3, just arbitrarily. Here are the steps you do. Step 1, pick a random point. That's an easy step. So let's say we pick this one. Okay. Now, step 2 is what you do is you compute the squared distance between each point and the point you just picked. So let's say those are like d1 squared, d2 squared. Now what you do, these are non-negative numbers. Now what you do is you normalize them to sum up to 1. You divide by the sum. So you normalize them, you're going to get P1, P2 to Pn. Now we draw a point at random, but with these probabilities. So which points are going to have high probability? Well, a point that's far away obviously has higher probability than the point that's close. So maybe the second one we'll draw maybe is there. Now in the third step, we just repeat this. So I take each point, and now though I compute the distance to the closest center. So maybe this one is here, this one's here, this one's here, this one's here. We normalize them, get probabilities, and draw. Okay, and you repeat. Is that clear? It's very, very simple. The surprising thing about this is that if I look over the randomness of the algorithm, and if I look at the resulting clustering that arises, so let's let C be the points that were drawn according to this algorithm. I want to know how close am I getting to the true minimizer of the criterion. So when I write expected value, I mean expected value over the randomness, because there's randomness in this algorithm. And what these guys proved was that this is less than 8 log k plus 2 times the true minimum. Yes?
What is the benefit of picking these points randomly proportional to distance rather than just, say, picking the one that's the furthest away?
So that is another algorithm. That's called the k-centers algorithm, where you just, after you pick the first point, instead of picking it probabilistically, just pick the farthest point, then pick the next farthest point, and so on. That's also a viable algorithm. But I think the difference is that you can prove guarantees like this. Okay. And now, since k-means plus plus came out, not surprisingly, there was a flood of papers with various improvements, which actually get rid of the log k term. You can make this a constant. You have to do various things like pick some extra ones and do a few other things. You can, if you're interested, it's very easy to find all these extensions. There's k-means sharp, and there's k-means, I don't know, there's all kinds of, it's hard to keep up with it. But the point is that the problem one, which is that we can't minimize this thing, is in some sense been eliminated, because now there's ways of choosing things where, well, we can't guarantee we get the minimum. We can guarantee with high probability we get close to the minimum. However, can you think of anything bad property that this might have? Or even the deterministic version we just spoke about. Can you think of any unpleasant property that might have? Oh, I still think it'll do a good job, as good as you can do. I mean, that's a case where I think if the clusters are close together, this k-means cluster might not work well, but at least we'll get close to the minimizer. Yeah. Suppose, I have this, and then I have an outlier out here. Then we're almost certainly going to pick this as one of the centers. Now, is this a good thing or a bad thing? Because you might end up putting this in it, calling this a cluster all by itself. And some people would say, that's good. I want to find the outliers, and this algorithm has helped me do it. But some people would say, I don't think outliers should have such a big effect on my clustering. So it really depends on your point of view whether you think that's a good thing or a bad thing. It would be interesting to see if one could create a robust version of k-means plus plus that was less sensitive to outliers. And maybe somebody has. I just maybe might not have seen the paper. But that would be an interesting project, is can you create a more robust version of k-means plus plus where you want it to have this property that it's choosing things scattered around, but not too sensitive to extreme values. There would be some trade-off there.
I have a problem regarding to this inequality. The RCAT is a kind of random variable here, or
The randomness is only with respect to the algorithm.
the RCAT is like you are given a kind of fixed data set.
Yeah, it's exactly what I wrote before. It's this. And we're treating the data set as fixed.
So is this true for the population version?
This is not even referring to the population version. So that's a separate step as to how do we relate the sample version to the population version. This is just talking about how well can we minimize this criteria on the data set. Yeah. Okay, but at least this is, I think it's a good thing that this was a problem for many years, and at least there's some solution, or really now a set of solutions, to the problem of choosing starting values. Okay. Now let's talk about what is probably one of the biggest problems in k-means, which is how do you pick k? This is a really, really tough problem. Choosing tuning parameters for unsupervised problems is just intrinsically much more difficult. For classification and regression, we can always just check our prediction error and try to minimize that. For an unsupervised problem, it's not clear what we should do. We can't simply look at this loss function. We can't look at this and just minimize this over k, right? Because we're going to end up picking k equals to n, and that'll be 0. And that's not a problem with the sample. It's even true at the population level, that the population version of this even the population version of this just gets smaller and smaller and smaller. As I put more points down, every x is now going to be closer and closer to some center. This is going to decrease with k. There's no bias variance trade-off anymore.
Add some penalty to that.
You could add a penalty. That's certainly one of the many approaches. So just to get a sense for how unsettled this problem is I think there are every year new papers about how to choose k and k-means clustering. The fact that people are still writing papers about it means that it's somehow no one likes any of the solutions. Maybe it's really saying it's an unsolvable problem in some sense. So one solution is, yes, to add a penalty. Another solution, I'll tell you a common solution people use in practice, even though this is a little bit ill-defined, is if we look at this risk function, it's going to decrease as a function of k. And what people hope to do, and you often see this in books, is there'll be something like this. It'll decrease strongly for a while, then settle down. This is called the elbow. So instead of looking for a minimum, people often look for an elbow. All right, but let me tell you, this is really hard to do in practice. I mean, if your data have this nice, well-defined elbow, that's great. But I can tell you from personal experience, you don't get plots that look like this very often. It's usually very ill-defined. And so the notion of even defining an elbow is kind of vague and hard. It's hard to actually make that precise. And it just might not jump out like that. So even though in practice, I think a lot of people will try to look for an elbow in this plot of r hat, it's not really, and I'm not suggesting this is a bad thing to do. It's just that it's not going to be obvious in most data sets how to pick k. And by the way, I'm not going to go through every possible method that's been suggested because there are literally dozens, if not hundreds of them. I'm just trying to mention what I think are kind of the main methods. Okay, now, so perhaps one of the better ones, I think, is, I've referenced it here. It's a paper by Lou Hayes, Nobel, and Marin in 2012. It's a hypothesis testing approach. So what they do is they start, the method works like this. Suppose your data look like this. Okay, we start with one cluster. Well, that's pretty easy. Then they're going to say, once you've picked a cluster, they're going to fit a distribution. In fact, they're going to use a normal distribution. So all they do is they fit a normal to this. That's pretty straightforward. Now what they do is they look at the drop in this criteria. So r hat 1 minus r hat 2. From one cluster, then they run one step of k-means clustering. In other words, they run k-means clustering with k equals to 2. And now you get 2 of these. And you just look at the drop. And then how do they decide what's significant? Well, they take the null distribution to be the original normal, and you simply do a simulation. Under the normal distribution, if you fit a normal to this, and you repeatedly draw data, run k-means clustering with k equals to 2, and compute this drop, you're going to get some distribution, which they take to be the null distribution. Now you look at your actual statistic, and this is the p-value. So they're taking a normal over your data as the null distribution. The change in the k-means risk is the test statistic. And by simulation, you get the p-value. You simulate from the null distribution. And then what you do is you iterate. So if you reject the null hypothesis, now you have 2 clusters. Now you do the same thing within each group. It gets a little bit questionable here because you're going to fit a normal to this, but first of all, it's kind of it really should be a truncated normal, but they ignore that because that would get complicated. And there's also some randomness now in the, this is like a random hypothesis you're fitting because you're fitting a normal now to this data set, but this was chosen from an earlier step that was random. So it gets kind of heuristic after step number 1, but the idea is you can keep going until it's not significant anymore and decide when to stop.
Does the original setting, the initialization actually affect the entire?
There is no initialization because you're just fitting a normal to the whole data set. So
I'm thinking, what is the situation where this method might fail?
well, so does this method succeed or fail? It's a hard question to answer because there are no, what you'd like to be able to prove, so here's an open question for somebody in the class. Can you prove that they don't have any they have some theorems in the paper, but not really about, they only have theorems about what happens at step 1. But really you're going to repeat this. Can you prove that if the data had k well separated clusters, for example, that this thing would correctly stop when it found the k clusters? And that's an open question. Nobody's proved that. So this is really a heuristic algorithm. There isn't a proof that it's correct or when, everything's going to work under some conditions, so I should rephrase it and say, under what conditions would this algorithm work? But at least it gives you some notion of statistical significance of the clusters, even though it might be a little bit heuristic. So that's just an example. There's other methods that do hypothesis testing for clustering. They're all somewhat heuristic, and this is just one of the better ones, I think, but there's other ones as well. Okay, now I want to talk about another method. My final conclusion, by the way, is going to be this is an unsolvable problem. I don't think there exists a good way to pick k in practice. But I am going through what I consider to be the more popular solutions. All right, next let's talk about another idea. So there was quite a bit of activity for a while. Actually, let me draw it over here. Using a notion called stability. Here's the idea. People thought, well, if I pick a good k, then I should maybe get stable clusters. What does stable mean? It means if I split the data into two, run k-means clustering on both halves, maybe I should get similar results if I've picked a good k. And so stability, some measure of stability should tell me how to pick k. I want to pick k to get the most stable answer. And there's various ways we could measure stability, but just to say intuitively that we get the same or similar clustering on one half of the data as the other half of the data. The problem is this paper came out in 2006 by Ben David, von Luxburg, and Paul, which I think pretty much killed the idea that stability is doing what you want it to do. And it's all explained in this little picture here on page 24, which I'll put on the board for you. What this paper is trying to show is that stability and a good clustering are actually two different things. So let's look at these examples. There's a lot more in the paper, obviously, but I think these four examples from the paper really get the point across very well. Okay, so let's look at this example. You can see I've got three groups of data. All right. So the first example, top left, shows a case where I'm going to fit. So this is what the data set looks like. But suppose for whatever reason I picked k equals to 2. I decided I'm going to see if k equals to 2 works. Well, what's going to happen? Let's ask ourselves, what type of clustering are we going to get? So, many things could happen, but in one try, it could look like this. I could end up splitting it like this. So I could end up with a center here and a center here. That's a possible outcome of k-means clustering, right? I have to split it somehow into two groups. It could easily end up looking like that. But if I repeated this again, or if I split the data into two halves and repeated it, it's quite easy to see because of the symmetry. A tiny change in the data could easily have caused it to go maybe like this. Right? You could take this data set literally, perturb the data a little bit, and keep running k-means, and you could see you can make this jump around. This is a success story because this is showing you that k equals to 2 is wrong. It's unstable. So this is an example where stability is correctly showing you you've underfit the data. Okay? Let's look at another success story. Suppose the data look like this. Suppose I decide I'm going to fit k equals to 3. Well, presumably we're going to pick a point here, and then what's going to happen here is it's going to try to divide up the data. It might look something like this. So I'm going to get my Voronoi diagram is going to look like this. But again, imagine perturbing the data points just slightly. It's easy to see I could just break the symmetry the other way and end up doing the opposite, doing, say, this and this. So it's highly unstable. So this is another success story. We tried to fit k equals to 3, and a stability analysis would say, wrong. You shouldn't have used k equals to 3. So these are examples where stability is correctly telling you you're doing something wrong. In this case, it's showing you you're underfitting. In this case, it's showing you you're overfitting. That's the good news. Now let's go to the bad news. Actually, instead of drawing these down here, let me draw them up where you can see them. I'm going to do this. Okay. Here I'm going to fit, so the data look like this. Let's suppose intuitively k should be 3, but suppose I take k equals to 2. What's going to happen is we're going to probably pick something up here, something down here, and that's going to be pretty stable. You try it again, you're probably going to get an answer just like this. So here's an example where k is wrong in some sense. We're underfitting, k is equal to 2, but it's stable. We're going to get very similar clusterings. So stability analysis has failed to reveal that k is incorrect. And the fourth example is similar to the second one, where I have a small cluster here and a big cluster here. We would hope to get k equals to 2, but if I fit k equals to 3, we're not going to have that instability anymore. We're almost, with high probability, you're probably going to do this. So we are overfitting, but it's going to be stable. So again, this is a failure of stability. What they're trying to get across is that stability is really measuring something about symmetries in the data. See, it became unstable when there were symmetries in the distribution, not when you were choosing k wrong. And so this is all expressed as various theorems in the paper, but the pictures really show you what's going on. That somehow you can very easily construct examples where you would consider k to be incorrect, and yet it's stable, and vice versa. So I would say that that pretty much, to the best of my knowledge, I don't see much literature after that about using stability methods to choose the number of clusters. So how should you choose the number of clusters? Man, I don't know. I really don't know. There's no method that I find satisfying. And if you find one, you let me know. But I feel this is, to me, the most difficult thing in k-means clustering. To be honest, I think in practice, what I like to do is overfit on purpose and then merge clusters together. That makes it much less sensitive to the initial k, and it also helps you find non-spherical shaped clusters. But you still have to pick some sort of starting k, and I honestly don't have an answer for you how to do that. And to the best of my knowledge, nobody has a good answer to this question. There's lots of proposals, but I don't know of a good answer. Unless, does anybody have a favorite method that they like?
Like, it's not the general method, but aren't you usually using k-means as part of some larger pipeline, so you have some loss down the road somewhere that you can use, and you can do like cross-validation?
That's a good point. If your k-means is only one step along the way, maybe eventually you're doing some sort of classification problem, and this was some sort of dimension reduction or something you were doing along the way, and if there's a well-defined loss function further down the pipeline, then by all means, this is just another parameter you could cross-validate over. But if you're just doing a pure clustering problem, purely unsupervised, it's still not obvious, I think, how to choose k.
You mentioned this like overfitting and merging clusters. So if we take that to the limit where it's n, so that would be kind of like hierarchical.
Yeah, so these are called, so it's a little bit off topic, but these are called hybrid clustering methods. Let me explain how that works. This is not in the notes, but I'll just go back to Mickey Mouse here. So this is something I like to do in practice. It's called two-stage clustering or hybrid clustering. You purposely overfit. You take a k pretty big. That's pretty vague, but you take k pretty big. The point is you're not trying to take k equal to the number of clusters. You're just taking it to be some big number. So suppose here I take k to be like 10. What you're going to find out is you're going to get a cluster like this, a cluster like this, a cluster like this. Now you could do something like, we haven't gotten to hierarchical clustering yet, but you could do, let's just say merging. You could merge these clusters together, and you could see any sort of reasonable merging criteria will get you back this big cluster and these two small clusters. That will solve the problem of the fact that the clusters have different shapes, maybe, and also, like if even a ring, this would find a ring, and it should be fairly insensitive to the initial choice of k. But there aren't many theoretical results about that. That's kind of a practical thing, but I don't know of many theoretical results about that. All right, so the next thing, we're moving right along here, is something we've already covered, so we can skip it. But in case you've forgotten it, this is the theoretical result which says that if I could minimize the k-means criterion, but if I want to know now what's the true risk of that, if I evaluate the true risk of this random quantity, that is less than or equal to the risk of the best clustering. This is what I mentioned earlier, plus something of order k plus d plus 1 log n. And that's what we proved earlier in the course as an example of VC theory. If you've forgotten, I can't imagine how you would have forgotten, but I put the proof back here. So if you want to see the proof, I'm not going to go through it again because we've done this before. But there is a proof there. It uses elementary VC theory. And there's a few other results for you. But the good news is we can skip all that because we did all that concentration and measure stuff. It's probably a good one to review for the test. I don't know. Just to review VC theory and all that stuff. This does tell you something interesting, though, which is, and it's not surprising, right, that if I'm trying to find a large number of clusters, things get more variable. And also, if the dimension is big, of course, the problem is much harder. All right. Good. So now we've done, just to say, where are we in the big picture? Well, we've done density clustering, and now we've done k-means clustering. Let's move on to the next clustering. Do we have time? Yeah, we got time. Let's start. So the next method here on the bottom of page 26, I've called it here geometric graph clustering, although we'll see in a minute it's equivalent to something you may have heard of under a different name called single linkage clustering. Okay, but first I'll describe the geometric version. And you can see it here, a picture of it in page 28. All it is we form a graph. So what we do is we have a parameter epsilon. All of these algorithms have a parameter in them. And what we do is we create a graph. And if 2 points, and we're going to have some sort of distance. Often it's going to be Euclidean distance, but it doesn't have to be Euclidean distance. And if this is less than or equal to epsilon, we put an edge between xi and xj. We literally connect them together, and we form a graph. So now what we have is a graph with n nodes, one for each data point, and some edges. Some things are connected together and some things aren't. And we just find the connected components of that graph. And as I mentioned on Tuesday, there are various algorithms for finding the connected components of the graph. I use iGraph. It's a very nice program. It's available in, I think, Python and R and probably MATLAB too. Does everything you could ever want to do with a graph. iGraph will do it as far as I can tell. So you just give it the data and say, give me the graph where everything is within epsilon or whatever. It's very simple, and it'll find you the connected components and so on. And you get out your clusters. So in the example I have here, if I make epsilon at the right size, you can see these are sort of be connected. So these will kind of be connected, and so on. And you can see that there's one connected component, there's one connected component. Well, that was an easy example. That worked beautifully. Right? Another example where it works beautifully is that ring example, which causes so much trouble for k-means clustering. Well, you're just going to connect these guys together, and eventually you're going to see there's one connected component. So this is very easy and intuitive, but does anybody know what problems might arise with this type of clustering?
If you have two clusters, then there are some points between them.
Exactly. So if there's some noise scattered around, you can very easily form a link between these things. And you can see that on the page 30. I put an example with lots of noise. Maybe so much noise it's hard to see the picture, but it doesn't work so well. In fact, we're going to see that there's a theorem that says that this type of clustering is inconsistent. What do I mean by that? There was some hope for a while that this type of clustering would actually find correctly the high density regions until John Hartigan proved in somewhere in the 80s a theorem that shows that this does not consistently find the high density clusters. So it's an inconsistent clustering method. Again, it's simple and it's fairly fast, but doesn't quite do what we think clustering should do. There's another issue here, of course, which is how to choose the tuning parameter epsilon. And we'll come back to that when we talk about hierarchical clustering, because this is really a special case of hierarchical clustering. These geometric graphs, I have to tell you, though, the graph you get by connecting things that are close, it's called a geometric graph. They've been studied mathematically in great detail. So mathematically, these are actually very interesting objects. There's actually a wonderful book by Matthew Penrose that has all the wonderful mathematical properties of geometric graphs. But statistically, unfortunately, they tend not to behave so well. Okay. But when we think about it this way, what we're doing is connecting things that are close together. And that's really a special case of a more general idea. This would be the other. I would say that this next type of clustering is the main competitor to k-means clustering, which is hierarchical clustering. And those of you who have done k-means clustering have probably at some point done some version of hierarchical clustering. So how does hierarchical clustering work? There's many different flavors, but let's imagine. So the data are over here. Here's my data. But I'm just going to write a point down here for each data point. So probably if you've learned hierarchical clustering, the version you may have learned is agglomerative clustering, which is you look at your data and you find, say, the two closest points, and then you join them. So maybe that's this point and this point here, so that gets merged. And now you iterate this. But we need to have, now I need to compare not just points to points, but points to clusters. Like this is a cluster. What's the distance between this point and this cluster? Or more generally, once I've run this many times, I could have a whole bunch of clusters, and I might have a cluster here and a cluster here. And not only do I have to compare the distance between this point and this cluster, but maybe this cluster and this cluster. And so we need a definition of the distance between two clusters. There are various definitions, and I've written the three most common ones at the bottom of page 30. A very common one is to use the minimum distance. Given two clusters, just take a point in here and a point in here and say, what's the two closest points? That's called the single linkage criteria. You could also use the average, which is called average linkage, or you could use the farthest point, which is called complete linkage. So most clustering algorithms, you have to specify which of the three distances you want. And now you proceed iteratively. So I compare all the existing clusters, and I say, oh, maybe this point and this cluster are the closest. So now I'm going to merge those together. I'm not drawing this very well. Then maybe I merge these, and then maybe I merge these. And you get out this tree, which is usually called in this context a dendrogram. And this is just showing this process happening as we merge more and more and more things together until finally everything is merged into one cluster. So this is, do I have a picture of this? I didn't draw a picture. I don't know why, but what comes out of this then is this dendrogram. So it's a lot like density clustering in the sense that you don't necessarily get one clustering out. What you get as you move up is different resolutions of clustering. Okay? And in R, it's called hclust, hierarchical clustering. I don't know what the MATLAB command is. And what you get out is this tree, this dendrogram. You might think there's no tuning parameter in this procedure. And if all you care about is looking at the dendrogram, that's true. There's no tuning parameter, which is one of the nice things about it. But if you really want to decide, I want a final clustering, you still have to make a decision where to cut this thing. So there's still a parameter to be chosen. So hierarchical clustering is very nice. And if you use the single linkage criteria, it's exactly identical to what I just described over here. Unfortunately, as I mentioned earlier, and I think I have a reference to this in the notes. Yeah, Hartigan, 1981. You would imagine I have a density like this. What you would hope to get out is that for any subset of points in your data set, so suppose I have some data here, some data here. Here's a subset of points. Here's a subset of points. And you can see this corresponds to some level set here, and this corresponds to some level set here. You'd like to say for any pair of sets that are well-defined density clusters with respect to the true density, does the dendrogram eventually find them? Is there somewhere in the dendrogram where those two sets appear and they're separated, but they're connected within and separated? The answer, unfortunately, is no. The answer is that it's hierarchical clustering is inconsistent. It doesn't actually find the clusters. So that's an unfortunate aspect of why it fails. The intuition is this. If I asked myself, how would I find the density clusters? I would use density estimation, like we talked about. So does single linkage clustering correspond to a particular density estimator? Actually, it does. It's a density estimator based on the k nearest neighbor density estimator. We didn't talk about k nearest neighbor density estimators, but instead of using a fixed kernel when I do density estimation, you could use the distance to the kth nearest neighbor to do density estimation. That's very similar to kernel density estimation. It's just that instead of taking like a Gaussian kernel, you just take a spherical kernel and you go out until you hit the kth nearest neighbor. It turns out, this is an interesting exercise, you can show that single linkage clustering is identical to density clustering using a k nearest neighbor density estimator with k equal to 1, the nearest neighbor. And that intuitively that makes sense because we're connecting everything to its closest point. But taking a k nearest neighbor density estimator with k equals to 1 is the same as using a kernel density estimator with a bandwidth that's very, very small. Think of this as like a bandwidth. And what do we know about density estimators when you take h to be really small? They're not going to be consistent. So that's why I was trying to give this an intuitive explanation of why single linkage clustering or hierarchical clustering is an inconsistent clustering mechanism, because it's like doing density clustering with a very small bandwidth. Did that help? I know that I just summarized Hartigan's whole paper in about 30 seconds, but that's the basic idea. The price you pay for not having a tuning parameter is you don't get a consistent clustering. Seems like bad news I'm giving you with all these clustering methods. So what we'll do next week, although you see why I started with density clustering is because in some sense it actually works. Whereas you see with k-means and hierarchical clustering, there are problems with those clustering methods. So let's talk about next week. So next Thursday is the test. As I said, I posted practice problems. I posted solutions to the problems. Do we want to have a review class on Tuesday? Yes. Oh, because I was going to say, since the solutions are posted, we don't need to have a review class, and we can go on to the next thing, which is spectral clustering. But I heard enough yeses that I guess we'll have a review session. So what we'll do is I'll just take questions next Tuesday about whatever. Was somebody about?
Yeah, just real quick. In terms of a cheat sheet, given that you said we to study, we do the practice problems and homeworks, what would you suggest we put on that cheat sheet?
What should you put on that cheat sheet?
What sorts of things? Because there's a lot of questionnaires.
Well, keep in mind, I'm only going to put 3 topics on: concentration of measure, minimax theory, and prediction. And the test will not be a surprise. It'll be very similar to the practice test or the homework. So yeah, don't worry too much about the test. The test is just there to make you stop and review things because we've covered a lot of material. I'm not going to make the test hard. It's nothing to sweat about. Just review things, go over the practice problems, and I'll take any questions you have on Tuesday. So I guess we will do a review Tuesday then, and then we'll have the test on Thursday. There's only one midterm, so it's nothing to worry about. Any other questions? Okay, so then I'll see you next week.